class. So today we're going to talk about 11.2 series. I just did this and the audio didn't work, so I'm doing it again. So here you go. So an infinite series is just going to be a collection of like a sequence, but in terms of just writing the terms, we're adding them up, and it's going to go on to infinity. All right. Partial sums, and they're written with the subscript. So S sub, whatever the number of terms you're going to add. So S sub 1 would be the first term added. S sub 2 would give us the first two terms added. S sub 3 would give us the first three terms added, and so forth and so on, right? So then when we get to S sub n, it's going to be A sub 1 plus A sub 2 plus A sub 3 plus all the way to A sub n. And we can write that with our Riemann sums going from 1 to n, correct? Of A sub I. It's something that we've seen in the past, so it's nothing new or anything, but that's the way we write it, and that's the notation that we use. Now, one of the things that's cool is if our series adds up to a specific number, let's call it S, then that's going to give us convergence. Okay, that's very important. It's going to be convergence as it goes to a specific number S. Now, if that sum doesn't go to a specific number, let's say that it adds up and it goes to infinity or negative infinity, then we're going to say that it's divergent. And divergent just means that it doesn't come to one number. Okay, so that's the important piece there. All right, I'm about to take you down a rabbit hole. Now this is the geometric series, and so I think you should remember that between -1 and 1, the geometric series has a sum, right? It would converge, and that's something you've known from previous classes. So I'm going to talk about if the radius is 1, what happens, and then if the radius isn't 1, what happens. And so let me show you those two cases. So if r is equal to 1, then what we get is our S sub n would be equal to A plus A plus A plus A plus A, a bunch of them, right? And that would be, depending on how many terms we have, in this case it's n, it would just be n times that A, right? But if n goes to infinity, then that tells me that this answer is going to go to plus or minus infinity, correct? So that tells us that since the limit as n goes to infinity of this S sub n is dne, right? The geometric series here is going to be divergent, right? Because it doesn't go to a specific number. Okay, now the other case, if r isn't 1, meaning it could be something bigger than 1, because the in-between case has been talked about in the past. I'm going to show you how to show this one. So if S sub n is equal to A plus A sub r plus A sub, r, AR squared plus AR cubed, all the way to A r n minus 1, right? That's the geometric series. I'm going to manipulate and take that same series, but what I'm going to do is I'm going to multiply by r. So I'm going to go r S sub n is going to be equal to AR plus AR squared plus AR cubed plus AR n minus 1 plus AR to the n. All right. Now the manipulation that I'm going to do is I'm going to go S sub n minus r S sub n is going to be equal to the part on the right being subtracted, and we see that that's going to be A minus A sub r to the n. Just so you guys can see, this would cancel this one, this would cancel this would cancel this, and this would cancel this, and that's how I end up with that value. Then I'm going to factor out an s sub n, so I'm going to get 1 minus r is equal to a, oops, not a plus, a minus, it's going to be a times 1 minus r to the n. And so then the sum would be a times 1 minus r to the n over 1 minus r. And that's the case if r is not equal to 1. Now, I'll just give it to you from here so you have it. If you are between 1 and negative 1, this is the formula that you'll use to find your sum, okay? So the radius is going to be less than 1, we'll get this, and then if the radius is greater than or equal to 1, we see the thing is divergent. It's going to take off forever and ever and ever. It isn't going to come to some specific value. So just something I wanted to be able to show you so that you guys could see that. Pretty crazy. Just so you know, in the example that we had up here, as r to the n goes to 0, right? My n is going to take off to infinity. And I can talk about that more in class if you have questions about what I did there. But I can show that to you. Now I want to use this and make it practical for you so that you are all able to do work. So let's do an example. So if we have this geometric series, we can see it's alternating, right? Remember, the first term is always going to be our a. So a is 5, and now we need to see what's happening to each term. So remember, a is part of it times r. So then if that's 5, the next one's going to be, it's always a plus, so it's going to be 5 times something's got to be negative. It looks like I multiplied by 2/3, and that's the first one. Then the next one's got to be a square, so let's see if that's going to work for us. If it's a square, what is that going to be? 4. 4 times 5 is 20. 3 squared is 9. Yep. Now we know that r is a negative 2/3. Something that's so cool about that, since the absolute value of r is less than 1, right, from the geometric series, we know that this is going to be convergent. So isn't that cool? Since it's convergent, then I can find out what the sum of the series is. And so the sum of the series is going to be a over 1 minus r, which will be 5 over 1 minus a negative 2/3. And that's going to give me 5 over 5/3, or my sum is going to be 3. So we clearly see this is convergent, and the value that it's going to add up to is 3. It's crazy. An infinite number of numbers added and subtracted are going to come up to one number. All right. Now, this harmonic series problem is actually pretty cool. We want to demonstrate that this is divergent. And the way to show that it's divergent, I'm going to do it by showing a pattern. All right, and the pattern that I'm going to use is I'm going to do it in even terms, right? So that's going to be 1.5. S sub 4 would be 1 plus 1/2 plus 1/3 plus 1/4, correct? Oops, I don't need to do that. So that's 4 terms, but would you agree that this is bigger than 1 plus 1/2 plus 1/4 plus 1/4, right? And this side right here is going to be equal to 1/2 plus 1/2, which would give me 1 plus 2 over 1/2. Now, I'm not going to call it 2. I'm not going to add them up because I want to show you it's going 1, then 2. The next one that I would do would be S sub 8, and that would be 1 plus, oh Lord, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8. And again, that is bigger than 1 plus a half plus a half plus a half. Now, what I'm doing here is I rewrote this as 1/4, right? So these two 1/4 would become this additional half. And then here what I did is I changed these to 1/8. So I have 4/8, which would be the other half. And what happens is that ends up being 1 plus a half plus a half plus a half is equal to 1 plus 3 over 2. And we can see it was 1, 2, 3 halves. The next one then, and I won't get too crazy, S16, right, is going to be bigger than 1 plus a half plus a half plus a half plus one more half. And then what I did with the last 1/9 through 1/16 is I made those 16ths so that I would get 8 of them over 16, which would add up to a half. And what that ends up equaling is 1 plus 1, 2, 3, 4 halves. And then 32 would be 1 plus 5 halves. 64 would be 1 plus 6 halves. And what we end up seeing is if I have s to the 2n, that's going to take off to infinity because I'm always adding a half to it, right? Which is actually smaller than the original function. So if that's going to infinity, then n is also going to infinity. And so that tells me that my function, my s sub n term that I had, is going to diverge. One of the things that's interesting about this is I didn't use all of the terms. So I didn't use S1, S3, S4, S5, S7. I only used others so I could use the pattern to show that they diverged. And if they're diverging, something that's added to them is just going to cause it to diverge even more. So we end up seeing the harmonic series diverge. And that's what it's asking you to see. Feel free to ask me questions about this as well. But trying to absorb what I'm doing here. So remember, and I'll write this in a different color just so you guys can see. This half here came from me going 1/9 plus 1/10 plus 1/11 plus 1/12 plus 1/13 plus 1/14 plus 1/15 plus 1/16. That's bigger than me going 1/16 plus 1/16 plus 1/16 plus 1/16 1/16 1/16 1/16 1/16, right? This one is bigger than that one, and that one ends up equaling 8/16, which is a half. So all I'm doing is saying if I add something smaller and that is divergent, something bigger will be divergent also. That's the reasoning that's going on into this problem. Okay? I know it's a little bit weird, but that's the way it goes. All right. If a series is convergent, then the limit of the sequence is going to go to 0. So that's important. The sequence is going to go to 0. And then the divergence test tells us that if the limit as n goes to infinity of a sub n doesn't exist, or if it doesn't equal 0, then the series is going to be divergent. So I want to show this one to you real quick to use the divergence test. And here's how it works. So we have this series, right? And we want to make sure that either the limit doesn't exist or that it's not equal to 0. So if we get some number here as a value, then this thing's going to be divergent. So this is where it can get a little bit confusing for you in how you test. So when you take the limit as n goes to infinity of our sequence, right, or our series, we're going to get the limit as n goes to infinity of n squared over n squared, 5n squared plus 4, right? That's our sequence that we're going to get. And I were to divide everything by n squared, wouldn't I get 1 over 5 plus 4 over n squared? We know that this piece as I go to infinity is going to go to 0. So I'm going to get 1 over 5 plus 0, or 1/5. But 1/5 isn't equal to 0, right? Because it tells us up here if it's equal to 0, then it's kind of convergent. If it's not equal to 0, then it's divergent. So because of this, we know that the series, right? The series diverges. And that is what the divergence test will do for us. It's beneficial that way. Okay. Let's do one more problem in this area, and then we'll go from there. This is just rules for you where you can break down series. Here, it's if you have a constant, you can pull the constant out. If you have a difference, you can break it up into sums of two series being subtracted. And then if you have a sum of two series, you can do the sum of each series and then add them up. So I'm going to do one example for you. And I actually want to demonstrate the steps. So I'm going to do it in two pieces, right? I'm going to go the sum going to infinity of n equals 1 of 3 over n times n plus 1 plus, and I'm going to gap it so you guys can see clearly the work, of 1/2, 1/2 to the n. Now, with this first one, there's a 3 there. I can pull the 3 out, right? That's the rule that tells me that I can do that. And so I'm going to get this. And then what I'm going to do here is I'm going to break this down by partial fraction decomposition. And so by partial fraction decomposition, I'm going to get the sum from n from 1 to infinity of 1 over n minus 1 over n plus 1. That's partial fraction decomposition. It broke that up. And then I'm going to apply the sum so you guys can see it. So I'm going to get 3 times 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus dot dot 1 over n minus 1 over n plus 1. And then what you can see here is something pretty cool. This half is going to cancel with that half. This third is going to cancel with this third. The fourth will cancel with the one that's here. The 1 over n is going to cancel. And what's left is 3. And then we're going to do the limit as n goes to infinity piece, because we know what it's going to end up being, right? Our sequence is this. And this is where I'm using the divergence test on it. I'm going to get 3 times 1 minus 0, which is going to give me 3. Okay, now on the other side, because there's 2 sequences that were being added, we can rewrite this. See if I think it's geometric. And remember, geometric was a times r to the n minus 1. So that tells me if I need to write it that way, so it's feasible, I'm going to pull out a half, and I'm going to get 1/2 to the n minus 1. Well, what's so cool about that is now I know a is 1/2, and I know that r is 1/2. And since r is less than 1, we know that this converges. And so the sum of this, right, the sum of this is going to be a over 1 minus r. And so the sum is going to be 1/2 over 1 minus 1/2, which is going to be 1. And then remember, we're adding them. And so my answer is 4. So the sum of these two series added up is 4. This is 11.2 series. By all means, when we meet on Monday, please ask questions and we'll figure this out together if there's anything that you don't understand. But it should be very manageable for you. All right. I wish you all the best. Take care.